is actually finish part 1, and part 2 isn't very many. So I'd really like to get through part 2, so we'll see. Okay, so hopefully you guys got your feet wet using PV equals nRT for the homework, and I like doing it that way. Because now we're going to kind of take technology, is it working? We're going to kind of take some spins on PV equals nRT that you may or may not have run into before. Okay, so this is one of the spins where we're after density. Oh, maybe I was just going to write it on here. No, I'll write it. Okay, so I told you to go P is equal to V is equal to N is equal to T is equal to, right? And PV is equal to nRT, that's how they're related. So when this one comes up, you're like, okay, I got a temperature, 25 degrees Celsius, of course I'm going to have to go to Kelvin, and I've got a pressure, 1.22 atmospheres. And you're like, that's all I have. And it asks for what is the density, so question mark, density in grams of gas per liter. That it's, okay. Well, this is one of those problems where you see where we have volume and moles, okay? If I take volume and moles, in other words, actually I have it on this next slide. There's something called the molar volume or the molar density, and it is simply N over V. Now I know it's not G over V, but if we can get moles over volume, can you get from moles to grams? Yeah. And then you have grams over volume instead of moles over volume. So this is one of those where actually we are going to solve it and we're going to leave it in N over V. Now if you're like me, I really have to concentrate. My algebra, I don't know what it is, but I always divide the wrong thing or something. So if we want to kind of get this to N over V, we could what? Divide both sides by V. So PV over V is equal to NV RT, right? And then these V's cancel. And then I could rewrite it, and I need to what? Divide both sides by RT. It's starting to kind of look like what you guys do sometimes. And that's where we have the P over RT is equal to N over V. Oh, see, now I did something wrong. Yeah, I didn't. Okay, it matches. See, I just go cross-eyed with these ratios. So that's how that works, right? And that's all we're going to do here. And then we can use the molar mass of the gas to go all the way. And I think the gas was argon. So that should be pretty good. So here we go. N over V, the molar density, the molar volume, okay. We just need to take the pressure, which is 1.22 atmospheres, and we're going to divide by the ideal gas law constant R. Also in the denominator is going to be the temperature, but we have to fix the temperature, which is in Celsius, by what? Adding 273. I could put 273.15, but I don't have any decimals here, so that's not going to do me any good. So it's the same deal. Okay. All right, so here's what it looks like plugging in. The N over V, or the moles per liter, is equal to 1.22 atmospheres divided by 0.082058. That's the value for R. The units for R are liters, atmospheres per mole Kelvin. And then also in the denominator is the temperature in the Kelvin scale, which is 298 Kelvin. So it looks like round to 3 significant figures. There is uncertainty in that value of R, but that's a lot of sig figs. So round to 3 significant figures. See if you get the same thing I get. Three significant figures, I got 0.0499. and then units would be moles per liter. And the cool thing about this is that, one, you have to show your units, but two, if you show your units, let's see what cancels. So we have atmospheres up here canceling with atmospheres down here, okay? And then we end up with this sort of strange looking thing. Well, I guess units of Kelvin cancel with units of Kelvin. Then we actually, it's not so strange. In the denominator, we have units of liters over mole. So the way I think of it is, and again, I'm not a math teacher, I think of 1 over, and then I think of liters over moles. Okay? And I want to basically resolve this so it's no longer in the denominator. I can do that by basically taking it up and flipping it. So that's moles over liters. Oh, that's wonderful. So that is the molar volume, sometimes called the molar density. Why does it keep doing that? Okay. Okay, so we're not done. That's not grams per liter. We need to get to grams per liter just using the molar mass of argon. And that's what I'm doing here on this slide. We basically piggyback from that, and I would probably put 0.0499 moles over 1 liter. And then if I want moles to cancel, I'll be left with grams. And this is dealing with argon. I just look up what the decimal number for argon is. Okay, and that's what I'm going to use here. 39.95 grams per mole. Then moles cancel, and we're left with units of grams per liter. So that's just kind of another gas law problem. So round to 3 significant figures. I got 1.99 grams per liter. That's just another type of problem. So here's a fun one for you. Do you remember when, and we talked, was it unit 3, we did the thermodynamics and stuff, and we talked about the little knots. Those are standard conditions for thermodynamic problems, okay? And I said some of you guys have had gases before. Well, we have different standard conditions for gases. You're like, oh, why do we do this? I don't know why. Most notably to me, the temperature. The temperature for thermodynamics problems is 25 degrees Celsius. The standard temperature for gas problems is 0 degrees Celsius. You're like, really? The standard pressure is 1 bar for thermodynamic problems. It's similar. I think 1 bar and 1 atmosphere are close. But instead of 1 bar, it's 1 atmosphere for gas problems. So anytime they talk about standard temperature and pressure, STP, standard temperature and pressure, capitals, okay, for gases, they're talking about that temperature and that pressure. Now this is kind of, I kind of laugh because this took me a while to figure out, okay? But if we go ahead and substitute in a pressure of 1 atmosphere, let's go standard pressure, and let's go standard temperature of 0 degrees Celsius, and let's go ahead and for N, for our moles, let's go 1.000 moles, okay? So in that scenario, the only thing I don't know is volume. And so for whatever deal, that's why I brought the ball here today. If you have 1 mole, exactly 1 mole of any gas, and it's at standard temperature and standard pressure, then it must be occupying a volume of, 22.414 liters. That's it. And I was talking to Rex, and one of the maintenance guy, and he doesn't think this is 22. He doesn't think this is like 5 gallons. I think he's right, but it's supposed to be 5 gallons. Okay, 22.414 liters. Yeah, it's symbolic, I guess. Any gas. Okay, if there was 6.022 times 10 to the 23rd gas particles in here, if it was a temperature 25, which is kind of on the warm side. 0. If it was a temperature of 0, which is on the cool side, 0 degrees Celsius, okay, and a pressure of 1 atmosphere, this volume would be that. So that's all that is. So another twist, and that actually the STP is going to come up, that twist is going to come up again. So what if the number of moles are constant? Well, if the number of moles are constant, we can go ahead and put it with our R value. So basically, we can rearrange PV equals nRT and get the constant moles and the constant, which is R on one side. Okay. So if that's constant, then we have this kind of cool situation. These are called combined gas law problems. And I kind of say they have a state 1 and a state 2. Between the states, you're not changing the number of moles. They're fixed. They're like in a balloon. Moles of gas will neither come nor go. But you can change the pressure and the volume and the temperature till the cows come home. Okay? And between the two states then, state 1 and state 2, the combined, the product of the pressure and volume divided by the temperatures, it's going to be the same. So we have this P1V1 over T1 is equal to P2V2 over T2, where the little subscripts indicate the two different states. Again, N is constant in these. So let's do a problem. You're like, oh my gosh, could they put any more words to this one problem? Okay, I'm not a word person. So, when faced with this, you're going to see me just kind of digest the numbers. So if you read it a few times, you kind of see the state 1, state 2. So you say the gas is behaving ideally. Well, that's good. They give the original state, that's state 1, the temperature and pressure and volume with the original state. They say the temperature's changed. Okay, they don't give that new temperature, but they give the volume and the pressure of the new state, and they ask for the new temperature. So this is actually what it kind of looks like. This is all the stuff you know about the first state, P1, V1, and T1. It's easy to get this mixed up. And this is all the stuff you know about the second state, P2, V2, and T2. P1 is 32 millimeters of mercury, V1 is 33.5 milliliters, T1 is 12 degrees Celsius, P2, 353 millimeters of mercury, V2, 46.7 milliliters, T2, don't know. But now do you see where basically we have, of the 6 variables, we only have one unknown. So we have one unknown, one equation. We can get to T2 basically plugging in. And what I like to do is rearrange it. Some people go ahead and plug it in, and then you have, in this case, you'd actually have the inverse. And so I like to rearrange it, and I'll kind of show you what that looks like. Before I do that, I want to mention a few things. First off, we talked about how the temperature, the Celsius and Kelvin temperature scales are both metric, but the Celsius 0 doesn't mean anything. It's just like a passing through value, the Celsius. 0 on the Kelvin scale really means something. So that's kind of how I think of it. All of our temperatures when we deal with gases have to be in the Kelvin scale. So we got to fix that. Now, do you guys buy this? That since we aren't using R, and I'll show you how this is going to work, since we're not using the liters atmospheres per mole Kelvin, we can leave our pressures as millimeters of mercury. We don't have to convert to atmospheres. We can leave our milliliters as milliliters. We don't have to convert to liters. And that's exactly what we're going to do. But we got to fix our temperature. So here we go. Now to rearrange this thing, okay, I'm going to kind of show you how I would do it in my little inept way. I mentioned the other day kind of about crisscrossing across the equal sign. So you're going to see me kind of, what I say, flatten this out by kind of crisscrossing. So if I crisscross, I get what? P1, V1, T2, and I'm solving for T2, is equal to P2, V2, T1. I flattened it out. So in solving for T2, all I got to do then is divide what? Both sides by P1, V1. So now I get T2 is equal to P2, V2, T1. And I'm going to put divided by P1, V1. We good with that? so many subscripts, so many numbers. Pressure, volume, temperature, moles. And here in a minute, I'll go ahead and do one more thing. I'm going to actually kind of bracket these. Oops. I'm going to bracket these pairs of pressures and volumes. Okay. Whoops, sorry, one more. Any questions about that? Really easy to make a mistake there. You're in good company if you do, but you don't want to do it on your final. Or your grad entrance exam or whatever you're taking it for. Okay, so here we go. But do you see here in a minute already where I told you we can leave the pressure in millimeters of mercury? Look, they're going to cancel. We can leave the volume in milliliters. Those units are going to cancel, not the numbers, but the units. Temperature got to be in Kelvin. So here we go. It's P2 over P1. So 353 millimeters of mercury over 322 millimeters of mercury. V2 over V1. So 46.7 milliliters over 33.5 milliliters. And then our Kelvin temperature, T1, 285. 285 Kelvin. Millimeters of mercury cancel, milliliters cancel. We're left with units of Kelvin, which is wonderful. I think here in the end, though, we're going to kind of clean up those, did I say Kelvin? Yeah. We're going to clean up those Kelvin back to Celsius here in a minute. Okay, so 3 sig figs, I get 436 Kelvin. And I have to go a few slides ago when the original question was asked, but it sounds like what it asked for, what would be the temperature in the Celsius scale. So now instead of adding 273, we subtract 273. I had to concentrate. So if we subtract 273, we'll get our Celsius temperature, which is 162 degrees Celsius.
It's not 163.
I don't know. It seems like it should be.
Is it the 0.15 getting rounded or something?
I'd have to track that down. Rhonda's right. It seems like if you put this in your calculator, it should be 163. If I used maybe the unrounded value.
Are you doing just 273 instead of 273.15 because it's all 3 sig figs?
No, nothing to do with sig figs. Since I'm subtracting, I can make that assumption because it's decimals. Those 0.15 would not do a thing because I'm rounding according to decimals.
273.15 comes out
I have my calculator.
162.85.
What's that?
If you use the 273.15.
Yeah, that's not the difference. What might be the difference is this value right here. I don't know.
I get 163 if you just do 436 minus 63.
Right, and that's exactly what she's saying. And I guess my slides are wrong, so the queen is wrong. But I don't know. I'd have to track it down why. So.
It'd be the ballpark though, right?
Yeah, yeah. If you wrote 163, I'd say you're right. So that was if the number of moles don't change. Well, what if the number of moles don't change and the temperature doesn't change? Your life just got simpler. So now P1V1 is equal to P2V2. What if the number of moles don't change and your volume doesn't change? Then your life got simpler, okay? And if the pressure doesn't change, these are all just variations of the combined gas law. Okay. So these will be due. We'll take a look at them. I'm not sure if we're going to go to the next part. We'll have to see. I think we might have to bail on it and just have you suffer next week. So 623 looks like this. Now, some of these hints, you wouldn't necessarily go this route. This is another type of chemistry problem where there's more than one ways to get there. But I'll kind of show you how I would think of them. So this looks like a combined gas law problem. A couple of states there. When you plug in all the stuff you know, it's kind of straightforward. Okay. Solving for V2. Whoops. My thing just froze. Okay. My circles there are just to remind you have to fix those temperatures to Kelvin. Another one, I'll just put this whole thing up here. Let's see, this one had a little bit of a twist. They didn't give you moles, and you don't even know what the compound is, but you were given the mass of 10 grams in state 1 and the mass of an additional 2.5 or 12.5 grams in state 2. So if you go with a generic molar mass, you should still be able to solve for the second pressure. I think I'm boring you guys. So this one goes back to a molar mass, okay? So the orange just means you have to fix the millimeters mercury to atmospheres, you have to fix milliliters to liters, you have to fix degrees Celsius to Kelvin. That's what the orange circles mean. Notice that we have enough information to find N. This is a classic problem where basically you are given the mass of the gas, oh, that rhymes. And if you can find N, then the molar mass is just moles divided by grams. And that will give you what you're after. It's kind of a classic. The next one, what's the molar mass? If you have a substance, I'll go ahead and back up to this one. If you're given, okay. So notice for this one, you are given its density in grams per liter. I think we've done this when we did concentrations before. If we set as our basis 1.00 liters of material, of gas, then by definition, we know we're dealing with a mass of 0.841 grams. Okay, so the pressure was given. Now our volume is 1 liter. Why? Because we set that as our basis. We don't know our number of moles, but the temperature was also given. We can get to the moles now, N, and it's kind of like it was before. Once you have N, then you can get to moles, or excuse me, then you can get to grams per mole, the molar mass, just by dividing, make a quick division. This is another one where you're given a physical constant of the gas. It's 1.80 grams of nitrogen per liter. If you use as your basis 1.00 liters, of course that's going to be your volume. And you're supposed to knock out the pressure. So number of moles you can get from the mass and the molar mass of nitrogen. Of course, the temperature you're going to need to convert to from Celsius to Kelvin. There's one more. Are you serious? Okay, one more. Again, it's given a physical property of the gas, the mass per liters. So we're going to consider 1.00 liters of gas. That's going to be our volume. Based upon, by definition, then, our mass of our gas is 2.56 grams. Temperature and pressure are given. We can get to moles from using P equals nRT. After we fix to atmospheres and Kelvin, we can get to moles. And then one last thing to get the molar mass is we take those moles divided by that volume. We take that mass, divided by those moles, grams per mole. And then the last thing they want to know is, or one of the things they want to know is, in addition to the molar mass, what's the molar volume? And that is just simply moles per volume. So I guess that's it for today. Those will be due on Monday, and we'll do some more problems on Monday. Oh.
I'm sorry.
Oh, yeah.